You rely on IT systems every single day, don't you? I mean, sending an email, checking your bank balance, these systems are just, they're there.
Always expected to be.
Exactly. But have you ever stopped to think about the silent heroes behind the scenes, the incredibly clever concepts and strategies that ensure those systems are always available when you need them?
Yeah, we're talking about the invisible architects, the engineers fighting off outages, big ones, small ones.
It's a world where, like, planning for the worst is the job, right? And success means nothing dramatic actually happens.
That's a pretty unique challenge, actually. Success is silence.
It really is. So today we are taking a deep dive into the world of high availability, often shortened to HA.
And disaster recovery or
Yep.
Notorious.
DIR. Our mission is to sort of unpack the core concepts, look at the common pitfalls, and some really clever solutions that keep IT services running.
And what's fascinating, I think, is that we're pulling insights from a foundational text way back from 2006.
Yeah, 2006. Which really proves that many of the core principles for resilient IT, they're pretty timeless, aren't they?
They really are. It highlights that, while the specific technologies change constantly, the fundamental challenges, ensuring continuity, dealing with failures, the answers are often surprisingly consistent.
It's less about the specific box you bought last year.
Exactly. More about the underlying design philosophy.
So by the end of this deep dive, we hope you'll have cleared up common misunderstandings, maybe delved into the how of making systems robust.
And you'll be armed with the knowledge, really, to understand everything from basic hardware reliability right up to complex network stuff.
And this isn't just for the IT pros listening, by the way. Even if your company outsources its IT, you need to remember,
You can outsource the work, the operations.
but you absolutely cannot outsource the responsibility. It's still your business on the line.
So this deep dive, it should empower you to ask the right questions, maybe negotiate better contracts, especially when you get down to service level agreements, those SLAs.
Because knowing what to ask for and, frankly, what's even possible, that's half the battle, isn't it?
That's the critical distinction, I think. Understanding these principles lets you gauge the quality of service you're really getting.
And push for what your business genuinely needs to survive those disruptions.
Yeah, advocate effectively.
Okay, let's start with the ultimate goal behind all this tech, all this planning, business continuity. Where does IT service continuity fit into that bigger picture?
So think of business continuity as the big umbrella. It's about keeping the entire business functioning, no matter what happens.
The whole operation.
Right. IT service continuity is our specific part within that larger goal. It's making sure the IT services you depend on stay available within agreed service levels, even when things go wrong.
So it's the digital plumbing, basically, keeping the enterprise flowing.
That's a good way to put it, yeah.
Okay, so it's not just about servers blinking away. It's about the business processes they actually enable and keeping those going.
Precisely.
To do that, we first need to distinguish between different kinds of IT interruptions. Our source draws a really crucial line between minor and major outages. Let's start with the more common ones, the minor interruptions. These fall under high availability, or HA. What exactly is HA?
Okay, high availability is essentially your defense against the frequent smaller hiccups. Things like a single disk failing in a server, maybe a power supply going pop, or a network card just deciding it's had enough.
The everyday annoyances for IT folks.
Exactly. And the expectation here is that while a user session might get briefly interrupted, the service itself becomes quickly available again, usually through automated means, mostly. The impact should be minimal, short-lived.
So you might notice a blip, a pause, but the system just kind of rights itself, almost invisibly sometimes.
Ideally, yes,
Yeah.
that's the goal. The core idea in HA design is making sure that non-essential components are not a single point of failure, SPOF.
Miss BOF, right. Hear that a lot.
And that almost always means building in redundancy, having multiple bits of kit, so if one fails, another is ready to take over pretty seamlessly.
No, I often hear the term continuous availability thrown around. Is that the same thing as HA?
Ah, that's a great question. They get confused a lot. They're related, sure, but continuous availability is actually an extremely rare, very stringent subset of HA.
Okay, so it's like HA plus plus, Ben.
Kind of. It aims for truly nonstop, uninterrupted service where no component failure is even noticed by the user. Most of what we call HA realistically is about fault recovery, meaning systems are designed to recover quickly after a failure, even if there's a brief interruption. It's not necessarily absolute fault protection where nothing ever fails visibly. It's about resilience, mostly, not absolute perfection.
That makes sense. And how do we measure this resilience? Is it just like a percentage, the famous nines?
Yeah, the basic measure is uptime divided by the total elapsed time. So uptime over uptime plus downtime.
Seems simple enough.
But here's a subtle point. It's important. Even planned maintenance, like system updates, scheduled reboots, that counts as downtime against this percentage.
Oh, right. So even stuff you plan to do hurts your numbers.
Exactly. Which is why achieving those 5 nines,
Hmm?
99.999% availability, is so incredibly difficult and expensive. Every single minute counts, planned or unplanned.
Got it. Okay, so that covers the minor outages, the HA stuff. What about the major ones? That sounds a bit more serious.
That's where disaster recovery, DR, comes in. DR handles those really significant outages where operations just cannot resume on the same system or maybe even at the same physical site.
So you're talking fire, flood.
But it could be. But instead of fixing it there, you activate a replacement or a backup system, usually somewhere else entirely geographically separate.
And a disaster. It isn't just a hurricane or an earthquake, is it? I mean, it could be something internal.
Absolutely. And this is a critical distinction people often miss. A disaster is defined by the business damage it causes, not necessarily a physical catastrophe.
Okay, I mean, example.
Well, I once saw a situation, experienced admin, totally competent, but in a rush.
Yeah.
Accidentally ran a script on the production system instead of the test one. Wiped out critical configuration files.
Ouch.
Yeah, no fire, no flood, nothing dramatic physically. But for that business, it was an absolute disaster. Ground operations to a halt.
Wow. That's a humbling thought for anyone working in IT. So for DR, it's not just about the technology then. Human judgment, clear processes, they sound pretty vital.
Precisely. Because the circumstances in a real disaster are inherently uncertain, they're unusual.
Right.
You need good processes, you need human intelligence to adapt and make nuanced decisions. You can't just rely on purely automated responses all the time.
Makes sense. Things get messy.
Which leads us to two really critical metrics for DR planning. Recovery time objective, or RTO,
RTO.
and recovery point objective, or OPO.
RPO. Okay, lay these out for us. What are they? Why do they matter so much?
Okay, RTO, recovery time objective. That's the maximum acceptable time for an IT service to be usable again after a disaster has been declared.
So how quickly do we need it back?
Exactly, it answers. How long can we afford to be down? For a critical trading system, that might be minutes. For an internal HR system, maybe it's days. It depends entirely on the business impact.
Okay, and RPO?
RPO, recovery point objective, that's the maximum amount of data lost that the business finds acceptable measured in time.
How much data can we afford to lose?
Right. For example, if your RPO is 2 hours, you're basically saying we can only afford to lose up to 2 hours worth of data. If the disaster strikes, any data created or changed in the last 2 hours might just be gone.
And defining these objectives, this is where service level agreements, the SLAs, become absolutely crucial, right? Especially when you're distinguishing minor versus major outages.
Exactly. Think about it. Aiming for just 1 hour of total downtime per year for a 24/7 operation. That's incredibly hard because any plant maintenance, patching, whatever, has to fit into that tiny window.
Yeah, good luck with that.
But contrast that with, say, 99.99% availability, but only during business hours. Let's say 14 hours a day, 5 days a week. That still means only about 20 minutes of allowed outage during those hours annually.
Which is still tight.
Still tight, but crucially, it gives you much more freedom for planned downtime outside those business hours, like overnight or on weekends. That makes achieving those stringent requirements much easier and, frankly, much less expensive to implement.
So it's about being smart, really understanding what available means for your specific business needs and the trade-offs you're willing to make.
Absolutely. It's about precision in your requirements.
This brings us nicely to two guiding principles that seem to underpin all effective HA and DR strategies: robustness and redundancy.
Robustness is all about minimizing the potential for failures in the first place. The core idea is really simple. Keep it simple and straightforward. The KISS principle.
Ah, KISS. Good old KISS.
Yeah. A design should be as simple as possible and only as complex as it absolutely needs to be. If a feature, a component, isn't truly required for the core function, it's often just another potential source of failure. Resist that urge to over-engineer.
Avoid adding bells and whistles just because you can. And redundancy, that sounds more like just having a backup copy of things.
It's a bit more sophisticated than just a simple backup. Redundancy is about establishing managed resources, things ready to go, to continue operations when failures do occur.
Managed resources.
Yeah, it's not just blindly duplicating components. It's about intelligently building in repetition, like having two power supplies instead of one, multiple network paths, so that if one fails, the other is ready to take its place, often automatically, without manual intervention.
Okay, so it's the difference between, say, having a spare tire in the trunk versus having run-flat tires that keep you going.
That's a pretty good analogy, actually. Yeah.
Now, to understand where these principles apply across a whole IT environment, our source uses the concept of the system stack, a layered view of IT components. How does this help?
It's a really useful mental model. Helps diagnose problems, helps design solutions. It categorizes things from the physical environment at the bottom, power, cooling, the room itself.
Foundations.
Right. Then you move up through hardware, the operating system, then middleware, things like databases, application
The
servers.
stuff in between.
Exactly. Then the actual application software, and finally at the top, the user and the administration environments.
And failures can happen anywhere in that stack.
Any layer. And critically, dependencies always flow upwards. A problem in the OS affects middleware, affects the app, affects the user.
And what's often surprising, you mentioned, is that single points of failure, those STOFs, they can be hidden, right? Depending on how closely you look.
Oh, absolutely. A marketing diagram might proudly show redundant storage.
Yeah.
Looks great. But if that redundant storage relies on a single non-redundant file system inside it to manage the data, you've still got a hidden SPOF right there.
So it's about peeling back the layers, not just taking the brochure at face value.
You have to dig deeper.
And to put all this into practice, there's a structured approach, a kind of solution roadmap for designing these resilient systems.
Yeah, it's an iterative process.
Yeah.
Really common sense when you break it down. First, you list out all the potential failure scenarios you can think of. Start high level, then get more detailed.
Brainstorming disasters. Fun.
Yeah. Then you evaluate these scenarios. How likely are they? How much damage could they cause?
Probability versus impact.
Exactly. Then you map those scenarios back to your actual business requirements, those RTOs and RPOs we talked about.
Connecting the tech to the business need.
Right. Then you actually design the solution, using that system stack idea and dependency charts to guide you. And finally, this is key. You review the solution you designed against those initial failure scenarios you listed. Did we cover them?
And I bet there are feedback loops in there. Like, the tech team comes back and says, protecting against that specific scenario will cost $1 million.
And the business owner might quite reasonably say, you know what, maybe we can actually live with that particular risk, given the cost.
Happens all the time, I imagine.
Oh, yeah. Business owners frequently reconsider requirements when they see the price tag for bulletproof protection. It becomes a constant balancing act. Benefit versus cost. It's a conversation, definitely not a mandate from IT.
Speaking of costs, let's move into part 2. Real-world applications and practicalities. One of the biggest misconceptions I hear is about the true cost of outages. It's way more than just the repair bill, isn't it?
Way, way more. You've got the direct costs, sure, repair bills, maybe contract penalties if you miss SLAs, but then you have these significant indirect costs.
Like what?
Additional work hours for IT staff scrambling to fix things, delivery teams sitting idle because the logistics system is down, office staff who just can't do their normal work.
Okay, that makes sense.
But here's where it often gets gravely miscalculated. People equate those lost work hours directly with lost revenue.
That's a classic mistake. My team couldn't work for 2 hours, so we lost 2 hours of revenue. Simple math, right?
Not necessarily, no. Real lost revenue primarily comes from customers actually going to your competitors because you're down.
Yeah.
Or long-term damage to your brand reputation because you seem unreliable.
So it's about customer churn and brand value?
Mostly. While a call center or a factory floor might genuinely be idle and losing money directly, a lot of office staff will just pivot to other tasks, do admin work, maybe catch up later. The link isn't always direct.
So investing in HA and DR, it costs money up front, obviously.
Absolutely.
But it saves potentially vastly more in the mid to long term by preventing those massive damages. You mentioned the Comair example before we started recording.
Right, the infamous Comair airline disaster back in 2004. A software glitch, just a bug in their crew scheduling system, led to thousands of canceled flights.
Yeah.
The estimated losses were around $20 million.
$20 million from a software bug.
Yeah. That's a perfect, brutal example of how the cost isn't just about fixing the software, it's the downstream business impact.
So HADR is a strategic investment in business survival, really, not just another IT expense line item.
Well put, yes.
Okay, let's dig into the foundational layer, hardware. This seems like the most mature area for HA, right? We've been dealing with physical machines failing for decades.
That's generally true. Hardware HA solutions are pretty well established. But There's a paradox with modern hardware.
Oh,
While disks are faster, storage capacities are just exponentially larger now,
perfect.
which is great. But the time it takes to resynchronize data onto a new, very large disk after one fails, that also increases dramatically.
So rebuilding the redundancy takes much longer on bigger drives.
Exactly. And this actually impacts availability because your system is running in a degraded, less protected state for a much longer period during that recovery or rebuild process.
Huh. So bigger isn't automatically better for recovery speed then. That's kind of counterintuitive.
It is. Without careful design, larger scale can introduce these new, subtle vulnerabilities.
So what are some practical hardware redundancy techniques?
Well, things like N+1 power supplies are common. That means for n active supplies you need, you have one extra as a backup, ready to go.
N+1, got it.
And hot swappable components, drives, fans, power supplies you can replace while the system is running. But crucially, you need to test hot swapping these things under actual load. Not just in a quiet lab. See if it really works when the system is busy.
Don't just assume it works because the datasheet says so. Test it. And what's the silent enemy of reliability when it comes to hardware, according to our source?
Cables and connections. Always the cables. They're where intermittent problems love to hide. They're a nightmare to diagnose reliably because the fault might come and go.
The wiggle test.
Huh? Yeah, sometimes. Honestly, the fewer cables, the simpler the connections, the higher the system's overall reliability tends to be. It's often the boring, simple stuff that bites you.
That makes perfect sense. Now, when we talk disk storage, RAID levels inevitably come up as core to HA.
Yes, RAID redundant array of independent disks is fundamental, but you have to know your levels. RAID 0, for instance, it stripes data across multiple disks purely for performance. It offers zero redundancy.
So one disk fails in RAID 0.
All your data is gone. Poof!
Right, not HA at all.
Whereas something like RAID 10 combines mirroring, making identical copies, and striping, spreading data for both performance and reliability. You effectively have redundant copies spread across multiple disks.
Okay, RAID 10 is a common choice for reliability.
And a crucial element in any serious RAID setup is the hot spare drive.
The hot spare, explain that.
It's a disk that's already installed in the system, powered up, but not actively part of the RAID group. It's just sitting there waiting. If a drive in the active RAID set fails, the system automatically pulls in the hot spare to start rebuilding the redundancy immediately.
Ah, so it minimizes that vulnerable, degraded window we talked about.
Exactly. It reduces the time you're running without full protection.
Yeah.
It's a key detail that often gets glossed over when people just say, we use RAID.
It really is. But even with redundant disks, RAID, hot spares, there's still a critical, often overlooked single point of failure, isn't there?
Yes. The volume manager software and the file system itself. Even if your physical disks are perfectly redundant, if the file system gets logically corrupted, maybe by a software bug, maybe user error, your data is still scrambled across the whole system.
The data's there, but the map to find it is broken.
Pretty much. Which is why our source makes such a strong point, a crucial takeaway. There is absolutely no excuse for not using journaling for file systems.
That's a bold statement from 2006. Still holds true, you think?
Absolutely, 100%. Journaling is fundamental for fast, consistent recovery after crashes or power outages.
How does it work, basically?
Okay, before a change is actually written to the main data area on disk, it's first recorded in a special log, the journal. If the system crashes mid-operation, when it restarts, it can look at the journal, replay any changes that were fully logged as complete, and undo any that were only partially logged.
So it brings the file system back to a clean, consistent state very quickly.
Exactly. Without needing a full, incredibly time-consuming disk check scanning the entire drive. It's the difference between waiting hours for your computer to maybe boot after a crash and it just coming right back up cleanly in seconds.
No excuse not to use it. Got it. Okay, quick detour. SAN versus NAS. Storage area networks versus network-attached storage. That debate raged for years. Did one win, or is it still ongoing?
You know, their future dominance is still debated, and frankly, it's probably not a zero-sum game anyway. SANs typically use block-level protocols like fiber channel, optimized for direct disk I/O, often for high-performance databases. They're built for robustness.
Block level, fiber channel. Okay.
NAS uses file-level protocols like NFS or CIF-SSMB running over standard TCP/IP networks. Think of a shared drive on the network.
File-level standard Ethernet.
Right. Historically, SANs offered lower latency, better performance for demanding things, but the trend has been that many features once exclusive to SANs, like snapshots, replication, have been reinvented for IP networks, blurring the lines significantly.
So NAS caught up.
In many ways, yes. Today, good NAS systems often provide perfectly sufficient performance for many, many workloads, which leads people to question if dedicated SANs are still necessary outside of really specific, extreme high-performance cases, massive databases, maybe high-end video editing.
So the choice depends on cost, complexity, the specific job.
Pretty much. It's less about one being universally better now.
Okay, let's move up the stack to the operating system level. Failover clusters are a big topic here.
Yeah.
How do these work, and why are they so key for HA?
Right, failover clusters are designed to make IT services independent of the specific physical computer they happen to be running on at any given moment. Decoupling service from hardware.
Exactly. You have multiple servers or nodes working together. They monitor each other. If a hardware error or maybe a software crash happens on one node, the service it was running is automatically migrated over to another available node in the cluster.
So the service keeps running just on a different machine.
Yep. They essentially abstract away those underlying hardware problems, presenting a consistent service to the users, even if a machine underneath has failed.
Are there different ways these clusters are usually set up?
Yeah, you mainly see two common configurations. There's active-active, where services are distributed across multiple nodes, each doing some work. If one node fails, the others pick up its load.
Sharing the work, sharing the load.
Then there's active-passive. Here, one node is running the service of the active one, and another node is just sitting there, fully ready, but idle the passive or hot standby. If the active one fails, the passive one springs to life and takes over.
One works, one waits.
Right. Each has its pros and cons regarding cost, resource utilization, complexity.
What are some of the surprising single points of failure that can still bite you within these seemingly robust clusters? They're not foolproof, right?
Oh, definitely not. That's where the devil's in the details. Sometimes, believe it or not, the cluster software itself can become a single point of failure. A bug in the clustering layer could potentially bring down all the nodes at once.
Oh, that's not good.
Not good at all. Also, during changes or maintenance, it's easy for single points of failure to subtly creep back in without anyone noticing. Maybe misconfigured shared disk connection or a network path that isn't truly redundant after a change?
Human error during changes again?
Often.
Yeah.
And practical challenges include keeping configurations perfectly synchronized across all nodes, managing log files effectively, ideally using a central syslog server so you can actually figure out the root cause when things go wrong across multiple machines.
Piece together the timeline.
Exactly. And making sure your backup and restore strategies understand these logical cluster hosts, not just the individual physical machines.
And what about the applications themselves? Do they just magically work in a cluster, or do they need special handling?
They absolutely need special handling. Applications running in a cluster need robust and critically idempotent start and stop scripts.
Idempotent? What does that mean?
It just means the script can be executed multiple times, but it will still achieve the same desired end result without causing weird side effects.
So running start twice doesn't break anything.
Right. Or running stop on an already stopped service is fine. This is crucial for smooth automatic failovers because during a complex recovery, the cluster manager might try to start or stop a service multiple times as it figures things out. Needs to handle that gracefully.
Okay, that makes sense. Beyond clusters, what other technologies have really boosted availability in modern IT? Load balancing and virtualization jump out.
They're both huge, yeah. Load balancing, it's often brought in initially for performance, right? To distribute millions of incoming web requests, say, across a farm of web servers.
Spread the load.
But it has this incredibly useful side effect. It significantly increases availability, especially for stateless services like basic web pages. If one web server in the farm goes down, the load balancer just stops sending requests to it. Users don't even notice the service stays up.
So it's a performance tool that gives you HA almost as a free bonus.
Pretty much, for the right kind of service.
Yeah.
And virtualization, well, that's just everywhere now. A true hallmark of modern IT.
Hard to imagine IT without it.
And it brings massive HA and DR benefits. Virtualization builds these abstractions, virtual CPUs, virtual memory, virtual storage that hide the messy physical reality underneath.
Creates a nice clean layer.
Exactly. And its power for HADR is that it establishes independence from specific physical components. Services running in VMs can be easily moved, paused, restarted on completely different physical hardware.
Live migration, things like that.
Right. And crucially for DR, Entire virtual machines, or hosts, can be kept replicated but powered off on a backup system somewhere else. In a disaster, you can activate them incredibly quickly. Think VMware, Microsoft Hyper-V, or even the mainframe virtualization that pioneered these ideas decades ago.
That ability to quickly spin up VMs elsewhere is huge for RTO.
Massive. Game-changing, really.
Okay, moving up another layer. Middleware and applications. This is where the business logic really lives. First, quick definition. What exactly is middleware?
Middleware refers to those software components that sit between the operating system and the application itself. Things like databases, application servers, messaging queues.
The plumbing inside the application stack?
Kind of, yeah. They provide common, reusable functionality, data access, transaction management, communication between different parts of an application. They handle common complexities, so the application code can just focus on the specific business logic, not reinventing basic wheels every time.
Makes sense. And when it comes to database HA and DR, it's more involved than just running the database on an OS-level failover cluster, right? Databases have their own specialized tricks.
Absolutely. General OS clusters help, but databases have specific, highly optimized solutions built in or added on. You have things like multi-master database clusters, where multiple database instances can accept writes, and they replicate changes between each other.
So any node can handle updates.
Right, and for disaster recovery, the really critical technology is often log shipping or redo log shipping.
Oh, shipping. Sounds important.
It is. This is where the committed changes the database transaction logs are continuously streamed or shipped over the network to a standby database, usually at a remote DR site. Think Oracle Data Guard, Microsoft SQL Server, log shipping.
So the standby is always just slightly behind the primary.
Exactly. This allows for a very low, very precise recovery point objective, RPO, because typically you're only potentially losing the very last few transactions that hadn't quite made it across the wire when the disaster hit.
Yeah.
Very granular recovery. Okay. And application servers, what's the main HA challenge there? Is it similar to databases?
Not quite the same. For application servers, the things that often run the core business logic, a major HA challenge is managing session state.
Session state, like what a user is doing right now.
Exactly. Deciding what information about an active user's current interaction with the application can afford to be lost if the specific server handling their session crashes, versus what information absolutely must be preserved, maybe replicated to other servers or stored persistently somewhere to ensure continuity for that user.
Like the items in your shopping cart online. You don't want that to vanish if the server hiccups.
Perfect example. Do you replicate the whole cart instantly? Store it in a shared database. Just accept it might be lost in a minor failure. Those are the trade-offs you have to make based on the application's needs.
This sounds incredibly complex for, say, an in-house development team to build reliably from scratch for every single application.
Yeah.
I bet this is where a lot of companies get into trouble. You've absolutely nailed a crucial point. Our source text from 2006 made a very strong argument that is, if anything, even more true today. 99% of all in-house applications that need high availability should use this approach, meaning leverage robust, off-the-shelf middleware that already has HA built in.
Buy, don't build, for the HA part at least.
Exactly. Trying to build complex HA capabilities, state replication, failover logic, consistency checks from scratch within every single custom application. It's incredibly difficult, it's expensive, and it's massively prone to subtle errors.
The middleware vendors have already figured this out.
They've spent decades refining these complex HA features. Database vendors, app server vendors, they have specialists who live and breathe this stuff. They are far, far more likely to get it right than even a talented but generalist in-house development team tackling it for the first time. Use their expertise.
That's a really strong recommendation. And when you are testing these applications, whether custom or using middleware, it's not just about functional tests then. You can't just click buttons and see if they work.
Not for HA testing, no. Functional testing checks if it does the right thing under normal conditions. HA testing is about deliberately creating failure scenarios.
Chaos engineering, basically.
Kinda, yeah. Pulling network cables, crashing database processes unexpectedly, stopping essential services, seeing how the application actually recovers. Does it come back up gracefully? Does it handle inconsistent data states without corrupting everything? Does it log errors effectively so you can figure out what happened?
You're testing its resilience under fire, not just its sunny day behavior.
Precisely.
Yeah.
A different kind of testing entirely.
Okay, let's shift gears now into part 3, the broader landscape and operational excellence. And you simply cannot talk about IT infrastructure without talking about the network. It connects everything.
Indeed. Our source calls the network the most important infrastructure component. And it's hard to argue with that. Without reliable connectivity, even the most perfectly redundant, highly available server is just an expensive, isolated box.
It's the circulatory system, right?
Absolutely.
All
Of
right.
your digital enterprise.
So how do we make this critical component resilient? Redundancy in switches and routers seems like table stakes, I assume.
Yes, that's fundamental. Multiple paths, redundant core devices, and within local area networks, there's this spanning tree protocol, SDP.
SDP, I've heard mixed things about SDP.
Yes. It's designed specifically to provide redundancy by detecting and logically blocking redundant physical paths to prevent catastrophic network loops.
Sounds good. Prevents broadcast storms.
It does. However, if STP is misconfigured and it can be complex, it can itself create problems. It might block paths you actually need or fail to detect a loop properly, leading to unexpected outages. It's a powerful tool, but it demands very careful design and management.
The cure becoming the disease, a classic IT theme. What about the wide area network, the WAN? Especially connecting different sites, maybe for Dr. Rowe. What are the challenges there?
Oh, the WAN has its own special challenges. A big one is often the last mile, that physical connection from your building out to the service provider's network edge.
The cable coming into the building.
Right. That's frequently a significant single point of failure. One careless construction crew with a backhoe taking out the fiber optic cable down the street.
Mm-hmm.
That can cause days, sometimes even weeks, of outage. And you have a very limited control over it.
You're at the mercy of the telco and the digger.
Pretty much. Also, modern network virtualization, things like SD-WAN, while offering great flexibility, can sometimes make risk assessment harder because the underlying physical paths and their actual redundancies might be obscured from you.
It's all abstracted away.
Right. And a critical point for listeners negotiating contracts. Standard SLAs, service-level agreements with network providers often have penalties that are minuscule compared to your real business losses during a major outage.
So they might give you a credit for a month's service, but your business lost millions while it was down.
Exactly. The contractual penalty rarely matches the business impact. It's something to be very aware of.
That's a tough reality. Now, how can something seemingly simple like DNS, the domain name system, actually help with disaster recovery? Isn't it just for translating names to IP addresses?
It does that, but it's also incredibly crucial for DR, especially for public-facing services. The trick lies in manipulating the time to live, or TTL, values in your DNS records.
TTL, how long a record is cached?
Right. If your primary site goes down, you change the IP address associated with your service's domain name, like www.yourcompany.com, in your DNS records to point to the IP address of your DR site.
Okay, update the record.
Then, once the old record expires in caching servers around the internet, which is governed by that TTL value, new requests start going to your backup site. The key is to lower the TTL to something short, like a few minutes before you plan to do a failover or immediately after an unplanned one to ensure traffic redirects quickly.
That's actually quite a clever, relatively low-tech way to steer traffic during a disaster.
It's a fundamental DR technique for internet services.
What about firewalls and NAT, network address translation? How do they fit into the HADR picture? Any gotchas there?
Firewalls come in different types, from simple packet filters up to stateful inspection firewalls and application-level gateways. A key thing with stateful firewalls, the ones that track ongoing connections or sessions, is that they often lose that session state during a failover between redundant firewall units.
Meaning active connections might get dropped.
Exactly. Unless the firewall cluster has a mechanism to actively synchronize that state information between the active and standby units, which adds complexity and cost, users might have to reconnect. NAT, which is often done on firewalls, rewrites IP addresses. This used to cause more problems if applications insisted on end-to-end authentication using the original source IP, but fortunately, fewer modern applications are that rigid anymore, usually less of an issue today.
Okay. Beyond the core network gear, what other critical infrastructure services need their own HA and DR plans? The unsung heroes.
We often overlook the services that just allow everything else to even function. DHCP, the Dynamic Host Configuration Protocol.
Giving out IP addresses.
Right. That needs to be highly available. If new devices can't get an IP address they can't get on the network. DNS, as we just discussed, is the absolute core of network naming. An error in your DNS data, or the servers being down, can instantly make huge swaths of your applications unreachable.
Everything breaks if DNS breaks.
Pretty much. And then there are directory services, think LDAP, or more commonly Microsoft Active Directory.
User accounts permission.
Exactly. They provide that central information for user authentication, authorization, computer accounts. They absolutely need to be highly available. Fortunately, they typically use multi-master replication built in for their own HA, so changes replicate between domain controllers. But if your entire directory service somehow goes down, nobody can log in, nobody can access resources, game over.
So far, we've focused really heavily on the technology side of things. But the human element, the processes, the preparedness, that's just as vital, isn't it? Maybe even more so.
Oh, absolutely. You can have the best tech in the world, but if your processes are bad or people aren't prepared, it won't save you. Effective IT service management, ITSM processes are paramount.
Like incident management.
Right. Incident management is focused on the immediate fix restore service as quickly as possible. Get it back up.
Firefighting mode.
Pretty much. But then there's problem management. Its goal is different, to actually reduce the number and impact of future incidents by understanding the underlying root causes, often through formal root cause analysis, RCA, and proactively detecting potential problems before they cause an outage.
I love that idea of proactive problem management, finding the weakness before it breaks.
Yes. And honestly, you should actively reward employees for finding and reporting potential problems, for finding those hidden risks before they bite you. It encourages the right culture.
That's a great management tip. What about the CMDB, the Configuration Management Database? That sounds important for knowing what you have.
In theory, the CMDB is the dream. A single, central, up-to-date knowledge base of all your configuration items, your CI servers, software, network gear, applications, their relationships. A perfect map of your IT world.
That sounds amazing. But the reality often falls a bit short, doesn't it? Keeping it accurate seems like a huge challenge.
It often does fall short, yeah. Existing CMDBs frequently don't meet the detailed needs for HA and DR analysis because of granularity issues.
Meaning?
Meaning, it might track a server, yes, but maybe not the specific non-redundant file system on that server, or that one critical network cable path that everything depends on, or the version of that crucial middleware. The devil, as always when it comes to availability, is in those fine-grained details, and CMDBs often struggle to capture and maintain that level accurately.
So it's useful, but maybe not the complete picture for HADR planning. And what about changes? It feels like making changes is where things break most often, despite all the planning in the world.
This is where things get really interesting, and it's often where organizations are weakest. Here's the fundamental truth. Every change is a risk to availability. Every single one, no matter how small.
Wow. Every change. That's a strong statement.
It is, but it's true. Which is why robust change management is absolutely vital. Every non-trivial change needs a clear justification. It needs a thorough review, specifically looking for any new single points of failure it might introduce.
Did this change break our redundancy somewhere?
Exactly. It needs coordination with the disaster recovery system. You don't want to change in production to accidentally break your DR capability. It needs approval, usually by a change advisory board or CAB, and, most critically,
Let me guess. A backout plan.
a mandatory backup plan. Absolutely essential. You must know how to quickly and reliably undo the change if things go wrong during or immediately after implementation. That plan is your lifeline, and ideally, it should be tested.
Knowing you can hit the undo button quickly gives you confidence. And release management, how does that relate to change management?
Release management is about how approved changes are grouped together into logical release units for coordinated testing and rollout. It's managing the deployment pipeline for new software versions or significant configuration updates.
Bundling changes together.
Right. And similar to individual changes, every release needs a backout plan, and often a clearly defined point of no return.
Point of no return sounds dramatic.
It is, kind of. It's a predefined decision point during the rollout where you decide, if we're not successful by this time or if we hit this specific problem, we absolutely must execute the backout plan. Because continuing forward from that point would take too long, be too risky, or make rollback impossible. It's the ultimate safety trigger.
Plan for failure even during the rollout itself.
You have to.
Okay, this all sounds like a ton of careful planning, process, documentation. But what about when, despite everything, disaster actually strikes? Testing the DR plan and having command centers, those sound like the crucial steps that turn theory into practice.
They absolutely are. They are the culmination of all this effort. The critical importance of regular GR tests, maybe annually, maybe semi-annually, cannot be overstated.
Practice makes perfect.
And sometimes, You should even consider surprise DR tests to see how people react under real pressure without weeks of preparation. You need to practice, then practice some more, until the procedures are almost second nature, muscle memory.
And after you run a test or a real event, you need to get back to normal, right?
Yes, that's a crucial, often underestimated part. Resynchronization. After a DR test or activation, you need well-defined procedures to move data back from the DR site to the primary site, restoring normal operations and reestablishing your protection. It's not just about failing over, you have to be able to reliably fail back.
Closing the loop. Okay. And what about the war room or command center? That sounds intense, maybe a bit old school, but in a good way.
It is intense, and it's often old school for very good reasons. This is a dedicated physical space, ideally, set up for coordinating the disaster response. And crucially, it needs robust non-computer infrastructure.
Like whiteboards.
Exactly. Whiteboards, flip charts, markers. Because in the initial hours, maybe even days of a major outage, your normal digital communication systems, your network, your email, your shared documents, your ticketing system might well be down or unreliable.
Can't rely on the systems you're trying to fix.
Precisely. Good old management on walls, with information visible to everyone in the room, is often still the most robust way to keep everyone updated, coordinate tasks, track progress, and make critical decisions when every second counts.
That's such a great practical tip. Don't rely on digital tools when the digital infrastructure is broken. And I guess that extends to documents too. You can't rely on finding the DR plan on the shared drive if the network is down.
Exactly right, which leads to the need for a disaster recovery emergency pack.
A physical kit.
Yes, a physical box or binder. It contains essential documents printed out, contact lists, personal mobile numbers, vendor support lines, critical procedures, network diagrams, login credentials maybe, stored securely, obviously, because you absolutely cannot rely on having digital access to this vital information during a major outage. It's your paper-based manual for navigating the chaos.
The break-a-glass in case of emergency kit.
Essentially, yes.
Okay, could you just walk us through a quick, maybe prototypical DR project example just to tie some of these concepts together in a concrete way?
Sure, let's imagine a common scenario. A critical application server with is data on a file server and associated data in a database. How would we protect that?
Okay.
For the file server data, maybe application binaries, user files, you might implement file-level mirroring or replication to a server at the DR site. You'd likely add a trash can feature to this replication.
A trash can, like on my desktop.
Sort of. It keeps several previous versions of changed or deleted files for a period. This protects against accidental deletion or corruption. If someone deletes something vital or saves a bad file, you can quickly retrieve the last good version from the DR site's trash can. Huge lifesaver.
Protection against oops. Got it. What about the database?
For the accompanying database, you'd almost certainly use that redo log shipping we talked about earlier, sending transaction logs to a standby database server at the DR site.
Continuous replication.
Right. But maybe, just maybe, you'd introduce a deliberate delay of, say, 2 hours before the logs are applied on the standby.
Why delay it? Isn't faster better?
Usually, but the delay gives you a safety window. If some major logical corruption occurs on the primary database, maybe a bad application bug writes garbage data, or an admin drops the wrong table, you have a 2-hour window to notice it and stop the replication before that bad data gets applied to your standby DR copy. It protects against logical disasters, not just site failures.
Ah, protection against human error or software bugs propagating instantly. Clever.
It's a common technique.
Yeah.
And of course, all the IP addresses the clients use to connect to this service would be virtual IP addresses, managed by the cluster or load balancer.
So they can be moved easily.
Exactly. They can be seamlessly failed over and brought online on the DR systems without needing to reconfigure hundreds or thousands of client machines. And the failover procedure itself, that would be a meticulously documented, step-by-step checklist.
What would be on the checklist?
Things like a clear decision point, who declares the disaster, based on what criteria, cleanup procedures on the primary site, if possible, to ensure a clean cutover, rigorous checks of the activated DR systems. So is everything running? Is the data consistent? And finally, the step to actually activate user access, maybe by updating that DNS record we talked about.
All right.
Each step practiced, timed, and owned by someone.
Wow. Okay. So to recap this whole deep dive then, we've really journeyed through the intricate layers of high availability and disaster recovery, from the microscopic details of like hardware redundancy and journaling file systems.
Right up to the macroscopic view of organizational processes, change management, and those command centers with whiteboards.
And we've definitely seen how that text from 2006, astonishingly, still offers so much timeless wisdom. It really proves that the underlying challenges of keeping complex systems running haven't fundamentally changed all that much, even if the specific technologies look very different today.
The principles really endure, don't they? Anticipating failure, building in sensible redundancy, having clear, practiced processes, those remain absolutely paramount, regardless of whether you're running mainframes or cloud-native microservices.
For me, I think the big takeaway is that the ultimate challenge in HANDR, it isn't just about implementing the latest, coolest tech. It's got to be a holistic approach,
Mhm.
one that genuinely balances the benefits against the costs, that meticulously understands the dependencies between systems, and maybe most importantly, embeds a real culture of vigilance and preparedness throughout the organization.
It's about building resilience into the system and the team.
Right. It's about actively anticipating what can go wrong because, let's face it, as good old Murphy's Law constantly reminds us, anything that can go wrong probably will go wrong, eventually, over time.
Which brings us to a final thought for you, our listener. As you think about your own critical systems, maybe the ones you rely on every day, what's the single point of failure that you might be overlooking right now? Is there something hidden deep within a setup that looks redundant on the surface?
And maybe even more critically, beyond just having a disaster recovery plan filed away somewhere,
Yeah.
have you truly, honestly practiced your backout strategy for when things inevitably go sideways? Because knowing how to get yourself out of trouble quickly and safely is often just as important as trying to avoid it in the first place.